Hello everyone. My name is Tasuku Okuda from the Data Platform Office Data Engineering Center, Line Corporation. In this session, titled Unification of Divided Data into a Single Big Data Platform with more than 2,000 nodes, I will introduce the challenges of data fragmentation that Line's data platform is to face, what those challenges were, and how we solve them. Before I begin, I would like to introduce whom this session will be useful for. First of all, for so-called data engineer positions. Our data platform is huge and it's on-premise. I hope this will be a good opportunity for you to get to know how Line's technical approaches took and what sort of configuration that is. The next step is for those who want to manage data and promote use. Our data platform has a vision of storing all of Line's data. Therefore, we need to be able to manage authority and bring together many stakeholders. The project I am going to introduce was also carried out while engaging with a variety of stakeholders. I hope this will be helpful for you to understand what kind of approaches are available to promote the utilization of data. Lastly, for those who are using data for their services and businesses daily. The purpose of accumulating data is to verify facts based on the data and use it as an opportunity to improve our services faster and more efficiently. I believe that it is very meaningful to learn more about what the data platform organization is thinking and working on in order to improve the quality of its utilization. Naturally, people who do not fall under these categories are also welcome. So let's get started with the main part. This is the agenda for today. I will first introduce myself and data platform at Line and explain the issue of fragmented data and why it is difficult to integrate it. Next, I will explain how we at Line have approached this problem. I will explain from both technical and data management perspectives. Finally, I will conclude this session by introducing the result of those solutions and the next step in Line's data platform. My name is Tasuku Okuda from the Line Data Platform Office. I am currently an engineer manager in the data engineering team. This team is responsible for maintaining and operating distributed systems such as Hadoop and Elasticsearch, developing ingestion pipelines using Flink and Spark, and various other engineering tasks in data platforms. I joined Line as a new graduate in 2013, and I have been working on DVA for Line Game, developing data analysis of ETL, and managing pipeline and Hadoop. Most recently, I was a leader of Hadoop migration project. These are the projects that I am going to discuss today. This is the first section. I will introduce the data platform at Line. In this section, I will briefly describe the structure and scale of the data platform at Line so that you can get a sense of how the data fragmentation came about and how challenging it is. We call Line's data platform the Information Universe, or so-called IU. We have named the platform Information Universe based on a vision of accumulating all of Line's data and using it effectively in a variety of services, Based on this vision, we named it the Information Universe. In the following slides, I will refer to the current Line platform as IU. So, what is Line's data platform, IU? On smartphones, Line apps and family apps, and also the server logs and database information, and all these sort of service data is accumulated on IU, and not just storing data, but for utilizing the analysis and dashboard tools, as well as integration functions to provide feedback to the system. That is all done in IU. Let me briefly introduce the background of the IU. Before the IU, each organization had its own analysis environment, but the information was siloed, and it was difficult to utilize it regardless of the organization structure. In order to solve this problem, we decided to create a single analysis environment for Line, a single endpoint for system integration using data, and a single standard for data utilization know-how. By providing these singles, we wanted to make Line a simpler and more user-friendly data platform. This way, we want to accelerate the data-driven approach, which is one of Line's rules of conduct. IU was born this way. This is the overall picture of IU's data pipeline. On the far left are the various service systems from which data is generated. Kafka is used as data entry point. From there, we use Flink, a streaming framework, to provide real-time feedback not only to Hadoop HDFS but also to Elasticsearch and external systems. The database allows for periodic batch processing to be easily defined in the UI by services. Many of these processes are running on Kubernetes, which allows for easy scale-out even as the number of services increases. The data stored in Hadoop HDFS is analyzed using various engines. In the past, Hive was the main engine, but recently Spark has been accounting for more than half of all jobs. For ad hoc statistical processing, we use Trino, which used to be Presto, to enable quicker trial and errors. For service integration, we provide Data Hub, a tool to exchange data via REST API. Not every user who touches the data of IU is an engineer. There are those who do not have technical skills but want to see data that is useful for various services. For this reason, we use a variety of BI tools such as Kibana for Elasticsearch and Hadoop, as well as Tableau and Jupyter for using analysis result on a dashboard, are probably most famous. In addition, to meet various needs, there are Yanagishima, which can easily execute Presto queries, or Ashes, a notebook system that performs scheduling and visualization when Spark code is written, and Line Analytics, which automatically visualizes data when it is submitted. In order to analyze the data, it is essential to have a proper authority management and operational efficiency. To improve operational efficiency, we are using Central Dogma, a configuration management tool, GitHub integration, and Prometheus and Grafana for monitoring and alerting. We are using Ranger to manage permissions in an integrated manner, and to make them more sophisticated, we have developed a catalog tool called IUM to define data owners. Let's take a look at some numbers that give a sense of the scale of IU. First, some numbers that show the scale of the infrastructure. The capacity of HDFS is now over 400 petabytes. The number of servers managed by Data Platform Room, including Hadoop, Elasticsearch, Kubernetes, etc., is more than 5,000. The number of V core, which represents the scale of yarn, has reached 90,000. Next, let's look at the degree of data utilization in numbers. In IU, the unit of data produced by a service is defined by a Hive table. The number of Hive tables representing the types of data has exceeded 40,000. The total number of jobs per day for yarn, Presto, etc. is 550,000, and they're heavily used by various organizations for various purposes. And the peak data flow rate can exceed 17 million per sec. You can see with the IU that data is being used on a very large scale in line. Now I have introduced a data platform, IU at line. However, it was not an easy journey. This is because of the existence of fragmented data. In this section, I will take a deeper look at what fragmented data means, as title says, and why it is a problem. Earlier, I mentioned the background of IU. Before IU was established, there were two major clusters, data chain and data lake, which were managed by different organizations. Data chain was created as a data storage platform for messages, and data lake was created as a more advanced data analysis platform that included family services. However, as each cluster grew, their roles became more complex and intertwined. I wanted to combine data that is not available in one cluster, or the cluster is too busy during office hours, so I want to use another cluster, more and more users forcing themselves to use one cluster over the other. As a result, the data flow and business execution of lines data analysis became very complicated. Let's look at the problems one by one. There were three main problems. The first is that the metastore with a table catalog is separated from the other metastore, which makes it impossible to join tables. The second is that Yarn and Presto are running on their own, so they cannot share computing resources. The third is a break in privilege management due to the fragmentation of storage where data is stored. First of all, the problem of catalog, no join problem, so to say. Let's take an example of pseudo query to retrieve the users who are sending the most popular stickers and the number of stickers sent. Here, we are joining two tables. However, what if these two tables are in different clusters? Hive and Spark SQL currently support only one metastore. This means that the metastore information cannot be viewed together with the metastore information in another cluster. This has resulted in a considerable loss of analytical efficiency and the need to force exchange data between clusters. Data exchange was also a very costly operation from the perspective of authority management, as described earlier. Next, there was a computing problem. Resource cannot be shared. The number of machines and their specifications differ greatly between data chain and data lake. The ML team was using data lake, which meant that we were always short of computing resources. On the other hand, data chain had a large amount of data but plenty of computing resources. It was an uneven distribution of resources. However, it is not possible to say, well, let's reduce data chain and replace it with data lake. HDFS has different data and different tools to support it. Migrating machines also requires a certain amount of time for large decommissioning and recommissioning tasks. In addition, capacity planning of the cluster itself has to be done for each disk, CPU, and memory. It was a lot of work to do all this at a time. Thirdly, there was a storage problem, privilege rupture. As I mentioned in the catalog problem, data copying was routinely done in order to see data in one place. However, when you copy data, Hadoop itself changes. So there was a risk of changing the authorization system for each cluster. In addition, when changing not only permissions but also data itself, such as schema changes or data deletion policies, the same policies must be applied to both clusters. However, the procedure for adapting the policy may differ greatly from cluster to cluster. This was a major risk in terms of data management and also increased the operational load on the system. Now that you know what kind of problem data fragmentation causes, how do we solve this data fragmentation problem? We tried to solve it by creating a new cluster, what we now call an IU, and consolidating into it. However, is it really that easy to integrate such a large cluster? As expected, we found some challenges in integration as well. The first challenge was, how do we copy the data? In each of data chain and data lake, various users are creating data with various granularity. What will happen if all of them copy the data at once? Of course, data dependencies will be messed up, and the system will suffer from various troubles caused by the data. Also, disk CP, which copies data between Hadoop clusters, consume a lot of yarn resources depending on the size of the data. This resource not only consumes vCore and memory, but also causes increased network traffic, and in the worst case, may even affect services not related to the data platform. Another important question is who to migrate first. In Line, there are complex dependencies between analysis jobs and tables, and data is frequently exchanged between organizations. Therefore, it is quite possible that the data of the dependency source will be moved without permission and the system will stop working. This is a big problem. It was suggested that each organization should communicate with each other, but it will be quite costly to communicate, and it is not easy to do so when there are changes in the project plan. Therefore, it was necessary to ensure that the overall data flow would not be affected even if each organization did the migration somewhat autonomously. Where the active data is also an issue. In the early stage of this migration project, double write was proposed to split the streaming job and write data to each of the old and new jobs. However, with this method, there is a need to satisfy the consistency that both written data must be identical. This is a very difficult requirement to meet, and it is practically impossible to ensure it not only in the data platform room but also in the various services where the data is input. Of course, the more components you have to manage, the more it costs, and more importantly, virtually no one knows which one of the double write is the correct data. So, we need to think of a way to do something other than double write. So far, we have talked about the fragmentation of data and the difficulty of integration. I hope you have understood that there are various problems. So, we have come up with an approach for various situations.
In the next section, I will introduce these approaches. I will discuss two major categories of approaches in this migration project. One is a technical approach. This is an approach that makes a complex program or system simple. The other is the data management approach. In order to reduce the cost of migration for users, we try to migrate with as few changes as possible to the current state. First is the technical approach. This is broken into 3 aspects: storage federation, computing relocation, and catalog synchronization. This is what it looks like in the diagram. The metastore with the catalog function synchronizes the old clusters to the IU. Computing resources are redesigned for each IU data center from old clusters, which is a physical migration. Storage define old clusters and IU as the same level and make both of them accessible. Let's look at them one by one. First, starting from storage. For storage, we deployed federation, one of the features of HDFS. As the chart illustrates, federation enables access from a single HDFS client to multiple HDFS clients. That enables HDFS client of IU to access data chain and data lake of all clusters. With this method, we don't have to copy data or double write. And traditional directory structure and privilege system can be maintained. We can increase efficiency of disk resources. This time we deployed logic federation, and all clusters share the same disk physically, which made us to plan capacity easier. In IU HDFS, we deployed ViewFS that provided more transparent access between clusters, while we don't have to care about multiple clusters. Next is about computing. Specifically, it is about migration of Hadoop Yarn. Yarn also supports federation, but due to the actual resource allocation and queue design, we did not choose this method, but rather a large-scale physical move with IDC-level redesign. The diagram shows how it looks. We prepared a dedicated data center room for the new IU and physically relocated the servers from the data center where data chain and data lake was located to the new data center. In this part of the project, we worked with the infrastructure team and the transporters to plan the decommission, recommission, and adjusted the computing resources to minimize the service impact. This relocation was done in stages, dividing the number of units into 100 to 200 units. In this way, we are able to estimate how many resources were available in IU, data chain, data lake at each phase, and what jobs could be run if those resources were available, and based on that information, we were able to provide guidance to the users to be migrated on the timing. For example, the ML team was using a lot of resources on data lake. Therefore, the same resources are needed on the IU, but if data lake is decommissioned, it will affect the ML service. Therefore, we plan to start the migration from the data chain side first, where we had more resources, and then processed with the ML team migration in parallel. This relocation also allowed us to do capacity planning at the IDC level. We will increase the capacity of the network interface and revise the rack design. In this way, we review the system so that we can withstand future load increase. The data platform uses a very large amount of network bandwidth. By separating the data centers, we were able to separate the bandwidth from other services, reduce the difficulty of submitting high-load job, and easily isolate problems in the event of a failure. We also collaborated with a moving company for the relocation between data centers. It was a new experience for me communicating with a type of business that I don't usually meet in my daily engineering work. Another technical approach on this topic is hybrid Hive server 2. This is an approach to deal with the case where the yarn resources of the old cluster are decreasing, but the catalog migration is still not completed, and the metastore of the old cluster is still used. To handle this case, we patched Hive with Kerberos and other authentication-related patches, and we are able to prepare an endpoint that can use both at the same time, such as the old cluster for Metastar and IU for YARN resources. The last for technical approach is the catalog. This was a very difficult issue, and at first we could not find a good way to do it. When both the old cluster and IU had the same table information, there were very few cases where we could provide catalog access across multiple clusters like federation. At the time, catalog access across multiple clusters was feasible in Presto, but Hive and Spark were not yet ready to be officially offered, only proposed in Apache's JIRA. On the other hand, moving table information manually takes a lot of time and effort to organize the stakeholders, as we discussed in the problem section earlier. So we thought of developing a system to automatically synchronize each Metastar DDL event from the old cluster to the IU. We call this system Metastore Syncer. Here is the diagram. The line stores the table information in the Hive Metastore. In Hive, an abstract class called Metastore Event Listener is provided. By using this class, you can perform various processes triggered by events that occur on the Hive Metastore. In this case, I used Metastore Event Listener to trigger DDL events such as table and partition creation, deletion, and modification. When these events occur, they are covered to JSON formats and sent to Kafka. Here, there is a device that makes it easy to recover even when a network failure occurs. This will be described in the next slide. The events sent to Kafka are fetched by Kafka consumer called sync worker. Sync worker has logic for DB table filtering, name translation, etc., which are not required for IU migration. The rules for this conversion are managed and reflected using Central Dogma, a configuration management tool that is part of Line's OSS. After these conversions are done, sync worker writes to the Hive Metastore on the IU side. This is a sequence of Metastore Syncer flow. Let me talk about the merits and innovations of Metastore Syncer. First of all, this sync allows IU users to have their jobs available only on IU. They no longer need to go through the trouble of migrating their own tables and past partitions. This has made the migration much less difficult and has triggered a shift to IU. This Metastore Syncer is a streaming processing. When it is working properly, it reflects the data in almost real time, but system failures are inevitable. What would happen if one of the Metastore Syncer servers went down? In order not to lose data in such an event, we decided to send each event to Kafka via fluentd after writing it to a local file instead of directly processing it to Kafka from Metastore Event Listener. This is because we thought that local disk access was more credible than access over the network. Since output performance is good, we are able to suppress concerns about the performance degradation of the Hive Metastore due to the processing performance of the Metastore Event Listener itself. Another concern was that a particular table would update a large number of partitions. It was easy to imagine the troubles that a large number of Metastore events would delay the streaming processing and many tables would not be up to date. In order to minimize this effect as much as possible, Kafka partition assignment on the consumer side is based on the table. Thanks to this, we can now troubleshoot Metastore Syncer and easily discover what the event is that causes it. As mentioned in the previous chart, there is filtering and transformation logic in sync worker. There are many tables whose data itself was old and not necessary for IU migration. The main purpose of this function is to exclude these and help organize the IU side. We are also able to answer the need for users to manage both the old clusters and IU. With these technological approaches, we were able to create a situation where we could only use IU. However, no matter how new the environment is, it is not complete until the users of IU migrate to it. In addition, from understanding the system to the cost of the work, it is undeniable that the migration itself can be a burden. Therefore, we focused on minimizing the charges, changes, and lowering the migration hurdles through a data management approach. I'll break it down into these 3 specific points. The first is that it should be completed only by switching the connection destination. The second is permissions can be maintained from old clusters. The third is to divide stakeholders into tiers in terms of importance and complexity. First, let me describe the point of it should be completed only by switching the connection destination. Migrating the system while connecting to the old cluster and the new IU and determining which is the right answer is quite costly in terms of data integrity assurance and increased complexity. So I created a situation where just switch the endpoint or connection to IU and you will see the same data. The chart shows how it looks. First is about the data input. Thanks to HDFS federation, we have a configuration where data is not a problem even if it is in the old cluster. This means that the data input pipeline remains the same and no changes required. How will the data stored in each HDFS cluster be referenced? Thanks to Metastore Syncer, all the important tables of the old cluster can be referenced on the IU Metastore. The entities of these data are the same as the original data in the old HDFS cluster. In other words, since they refer to the same file, we can say that the data integrity is guaranteed. Putting all these together, we can use the data just like the old cluster by simply switching the connection to the IU side without worrying about the data integrity. Next is permission can be maintained from old clusters. If you prepare a brand new cluster, there is a risk that you will have to start the permission request from scratch or that you will not have enough permissions. Naturally, granting unnecessary privileges can cause a serious incident and should be avoided with the highest priority. This is accomplished through the integration of HDFS Federation and its associated permission management system, region, LDAP integration. Since the existing data is in the old clusters, these permissions will remain the same as before. The users of files and directories and their permission policies are also the same, so that there will be no trouble caused by permissions after the IU migration. Large Data Platform uses LDAP for user management and Ranger for permission management. Separate management of these two systems would not only increase management costs but also risk serious operational errors such as mismatched authorization policies. Therefore, we integrated Ranger LDAP into one so that all HDFS can be managed by one authorization system. The third is to divide stakeholders into tiers in terms of importance and complexity. At Line, various organizations are working autonomously. We believe this is a good thing, but the degree of dependency on the data platform, the connection between data and services, and the literacy and technical skills for data utilization vary within each organization. Also, as I said in the problem section, organizations are often dependent on each other for data generation. Therefore, instead of providing a uniformed guide for all the organizations, we kept the basic policy simple and provided customized migration procedures for each organization based on the importance of data platform. Specifically, we're thinking of this kind of tier. The top tier is the data platform, which is responsible for generating raw data and data that is widely used across the company. Then there are the machine learning and data scientist teams that use the raw data to generate more advanced data models, etc. And finally, the service side, which uses the data to generate data and manage dashboards that are closed to the service. By dividing the IU migration into these and migrating from the lower tier, we are able to minimize service problems such as data does not exist in the IU, my system is broken because of the migration of other teams. So, why does migration work better if we migrate from a lower tier? Let's assume that Tier 3, the end of the data generation flow, has migrated. Tier 1 and Tier 2 above it already have data on the IU side thanks to Metastore Syncer. Thus, Tier 3 users can generate data by simply switching to the IU side. At this point, there will no longer be any Tier 3 data in the old clusters. However, since there is no data generation dependency after them, their migration will have no impact on the rest of the organization. By reducing the dependency on the old clusters, you were able to decommission computational resources, physically move servers, eliminate unnecessary components, and organize the system. After all the Tier 3 have been migrated, we can do the same for the Tier 2, and the migration will be completed gradually. Here's a recap of the approach section. In this section, I presented the approach we took to achieve the IU migration from both technical and data management perspective. Technical approach includes storage federation, relocation of compute resources, and catalog synchronization. Data management-based approaches include it should be completed only by switching the connection to maintain the privileges from the old clusters and to divide the stakeholders into tiers in terms of importance and complexity. Through these, we have succeeded in lowering the hurdles of migration by simplifying a complex system and minimizing changes. As a summary of this session, I would like to conclude by introducing the results of this IU migration and the future vision of IU. Here's what we've learned through this IU migration. The first one is to understand the internal architecture as an engineer. It helped me to clarify complicated things and come up with simpler solutions. Second, as a platform provider, we should maintain the existing environment as much as possible. Change is a cost in itself. By identifying which changes were important, which could be maintained for the evolution of services, and minimizing the change cost for the evolution of service, the system impact was reduced. Third, simplicity will allow us to evolve large-scale systems and services. Complexity alone makes it difficult to tackle new things and makes the system more obsolete. Analyzing this situation one by one and clarifying the system will bring various benefits such as introducing new technologies and reducing the cost of developing tools that are easy to use. Regarding the third point, let me explain our next challenges. First is data democracy, the democratization of data. We're trying to make the IU wave more advanced and to promote the use of data while approximately managing the level of data security of existing IU currently. In this context, we hope to improve the efficiency of data dependencies and authority transfer by introducing Apache Atlas and providing data lineage. We are also trying to evolve as an ML infrastructure. We are planning to introduce Delta table using Iceberg to speed up the processes from data generation to utilization and to improve the performance of service integration. We are also planning to do capacity planning on a larger scale and make the infrastructure capable of performing well enough to do machine learning in various fields. We are looking for engineers who are passionate about taking on these challenges together, making IU better and accelerating Line's data-driven strategy. This concludes my session. Thank you very much for your patience.